This is PreAP PreCalculus Note Section 3.3, the Remainder Theorem and the Factor Theorem of Polynomials. This first video, we're going to focus on the Remainder Theorem. Let's read this together. If a polynomial function f of x is divided by x minus a, that's a linear function, then the remainder, if you divide the function by x minus a, is the same as whatever f of a is. So here's what that means. Let's say that a is 5. If I put 5 into this function and the answer is 4, if I take this function and divide it by x minus 5, the answer is also going to be 4. Let's look at just a small example here, reviewing synthetic division. We'll try to make sense of the remainder theorem. First of all, whatever we're dividing by, this linear, let's set it equal to 0 and solve it. If we set it equal to 0 and solve it, we're going to get x is 1/2. So in the case of the remainder theorem, we are saying that x is 1/2. I'm sorry, we're saying that a is 1/2. So if we divide this synthetically, which I don't know if you remember how to do or not, take the coefficients of the terms in descending order. If we're missing any terms, we got to put zeros in. We're not missing any terms. So we got 2, 1, -13, and 6. We're going to divide that by 1/2. This 1/2 is coming from taking whatever your linear function is you're dividing by and set it equal to 0 and solving it. It's what would make this equal to 0. 2 times 1/2 is 1. 1 minus 1 is 0. Then, to divide synthetically, we put a 0 in this first spot or leave nothing there, add these, and we get 2. We then multiply 1/2 times 2 and put the answer here. That's 1. We add these, and we get 2. We multiply, put the answer here. 1/2 times 2 is 1. We add these, we get -12. Multiply these, put the answer here, we get -6. We add these, and this last thing we get is the remainder. So we would get a remainder of 0. So here's what the remainder theorem is saying. If you were to take a 1/2 and plug it in here for these x's, you would get the answer of 0. If you were to take this and divide it by 2x minus 1, you'd get a remainder of 0. That's what the remainder theorem is. The conclusion that we can draw from this, therefore, 2x cubed plus x squared minus 13x plus 6 divided by 2x minus 1 is equivalent to 2x squared plus 2x minus 12. Let me explain. First of all, this divided by this was the original question, and this is the original question. It's equal to this because once you get this polynomial here, it's called a depressed polynomial. Once you do the division, this is the lead coefficient, second coefficient, and this is the constant. And determine what variables here go here and with what exponent. It's the same variables as the original problem, but you subtract 1 from each of these exponents. So instead of being cubed, it starts out as squared, and then to the first, and then to the 0. Before we get into these test and quiz-like questions, let's look here and try to determine, does the remainder theorem actually work? For each of the functions in the table below, there's only one function here, use a graphing calculator to determine the given functional value. Then use synthetic division to determine the remainder. So we're going to try to figure out, is the number we're going to get by plugging the number 1 into this, is it actually the same as the remainder if we divide by this? So I took the liberty of putting this function, I think I did, of putting it into Desmos. You can see that it's here. I'm going to convert this to a table can do similar things on your graphing calculator. And if you don't know how to do that, let me know and I will show you. So if I put a 1 in, I'm supposed to get 0 for an answer. That's what it's saying. If I put 1 in, I get 0 for an answer. So that means here, calculator's telling me that P of 1 is equal to 0. Now let's see if the remainder theorem actually works. The divisor, x minus 1, comes from whatever this a value is here, 1, it's always x minus that a value. The a value is 1. You set that equal to 0, the divisor, and you solve it. That tells us we're going to divide by 1 synthetically. So we got 1 we're dividing by. Our coefficients are 2, 7, 4, -7, and -6. If I divide this, whoops, add 2 and 0 and get 2. 1 times 2 is 2. Add, I get 9. 1 times 0, 1 times 9 is 9. Add, I get 13. 1 times 13 is 13. Add, I get 6. 1 times 6 is 6. This last box is the remainder. It's 0. So sure worked for this one. P of 1 is 0. If you divide function p by x minus 1, you get a remainder of 0. Looks like the remainder theorem is working. If I put a 2 in for this, I'm supposed to get 84 for an answer. It says the ordered pair is 284. So I would expect if I divide p by x minus 2 synthetically, I should get 84 as the remainder. If I set this equal to 0 and solve it, I'm going to get x is 2. So I'm going to divide this synthetically by 2. And let's see if we get the proper remainder. It's supposed to be 84 according to the remainder theorem. I add 0 and 2, I get 2. 2 times 2 is 4. Add, multiply, add, multiply, add, multiply, add. Remainder is 84. You don't have to write R, remainder is 0, remainder is 84. I just put it here from fastest. What about -3 if we put that in? If I put -3 in, I should get 24 for the answer. So if I divide this polynomial p by x plus 3, I should get the remainder of 24. Let's see if that works. Synthetically, I'm dividing it by -3. We add and then multiply. And we add and we multiply. And we add and we multiply. And we add and we multiply. And I got a remainder of 24, just what we expected. What about something harder like -3/2? Put this in my calculator. -3 divided by 2. Should get 0 for the answer, it says. So let's see. If I take 2x plus 3 and set it equal to 0 and solve for x, I should get a remainder of -3/2. I'm sorry, that's not true. I'm going to divide it synthetically by -3/2. I should get a remainder of 0 because this is saying it's 0. So I'm going to divide this synthetically. Don't freak out that we have this fraction. No big deal. No big whoop, as the kids are saying these days. Add. When you multiply a fraction times a whole number, you multiply the numerator by the whole number and then divide by the denominator. Or you could say, I'm going to take the whole number and divide by the denominator and then multiply by the numerator. Well, the 2's would cancel. We would get -3. And we add. -3/2 times 4. 4 divided by 2 is 2. 2 times -3 is -6. And then we add. -3/2 times -2. The 2's cancel. So we have -3 divided by -1. That's +3. And we add. Multiply these little fellas together, we're going to get +6, and we add, we get a remainder of 0, just like we expected. So guess what? It sure appears as though the remainder theorem works. Now let's look at some examples of what might appear on tests. There's different ways to do this. I'm going to plow through this in one way and perhaps talk about a different way that you could do this, which will be acceptable. For what value of k will the function p of x have a remainder of 8 when divided by the factor of x plus 2? So here's what we could do. We could divide this by x plus 2. If we divide it by x plus 2, synthetically, means we're going to be dividing by a negative 2. If I take the coefficients, negative 2, k, and negative 2, we would like to have a remainder of 8. Let's see what happens if we do this, and then we'll try to reason this out. Synthetic division, add, multiply, add. Now when I multiply negative 2 times 2, I get negative 4. That's no big deal. These are not like terms, so when I add this, I'm going to get k minus 4. To show that it's all one thing, I'm going to put it in parentheses. Negative 2 times this is going to be negative 2k plus 8. When I add these, I'm going to get a remainder of negative 2k plus 6. So here's what we're saying. This is the remainder when we just did this division. We would like the remainder to be 8. This is the remainder. We would like it to be 8. So that just tells me we need to set this equal to each other. Negative 2k plus 6, we're going to set it equal to 8, and we're going to solve for k. We get k is negative 1. If k was negative 1, this would give us the proper remainder that we're looking for, which is 8. Number 2, we would like this to have a remainder of 0. And let me show you an alternate way to do this. This is method 1. This would be method 2. Both are acceptable. So let me show you method 2. For what values of k would this function have a remainder of 0? According to the remainder theorem, if I plug in to this the a value, and the a value here would be negative 1. If I plug negative 1 into this, in for x, here, and here, and here, this should give me the same answer as if I divided it synthetically, the remainder. So in other words, I'm going to take the remainder and set it equal to negative x squared, x to the 4th, minus 2x squared plus kx minus 6. We're saying that remainder is 0, and the a value that I'm using for this is supposed to be negative 1. Negative 1 to the 4th is a positive 1, and then there's a negative on the outside, so we change the sign. Subtract 2 times a negative 1 is a plus 2. Negative 1 times k is a negative k, a minus 6. Combine like terms. Negative 1 and 2 is 1. 1 minus k is a negative 6, or negative 5, so we get negative k minus 5. If I add 5 to both sides, did I make a mistake here? Let's see. We get k is negative 5. Let me do this using method 1 and see if we get the same answer. If we don't, then I've made a mistake. According to the key that I have written here, I have made a mistake. I'm going to divide by negative 1. The coefficients of negative 1, 0, and negative 2, k, and negative 6. Now you might be wondering, where's this 0 coming from? We are missing between these two terms an x cubed term. We're missing it because the coefficient was 0. 0 times x cubed was 0. We don't typically write that, but we need this placeholder. So let's see. Add and multiply. add and multiply, add and multiply, add, don't have a lot of space here, if I multiply, I get negative k minus 3. I did make a mistake someplace. If I add these, I'm going to get negative k minus 9. If I set that equal to 0, I'm going to get that k is negative 9. But here I got that it was negative 5. So I made a mistake over here. You may know what that mistake is. I don't. Let me check my signs. I have a negative, negative, positive, negative. So that's fine. Somehow this should be a negative 2. Oh, I see what my mistake is. This right here is k squared. I did not square it. So when I square this, let me just bring down what I did wrong. I'm going to end up erasing it. So when I square this, it's going to be negative 2 times 1, which is then going to give me negative 1 minus 2 minus k minus 6. Negative 1, subtract 2, and a subtract 6. Well, that's going to give me a subtract 9 minus k. And this gives me k is 9. So remainder theorem works as long as the person that's doing the problem doesn't make a mistake. And I made a mistake right here by not including that squared, which then affected this sign, which affected this, which then changed this to a 5 instead of a negative 9. So it does work. There are two different methods. To be clear, this is method 2 here. This is method 1. You don't need to do both methods. Like, you should be proficient in both methods, but don't use both methods for the same problem. All right, last one with the remainder theorem, and then we'll make another video after this for the factor theorem. Suppose the function g is divided by the factor x minus 2. Which is greater, the value of g of negative 2 or the remainder of g of x when it's divided by x minus 2? Now you can do this in different ways. You can use method 1 or method 2 for this. So my choices are, in both cases, if x minus 2 is a factor, then that means the a that I have here is actually 2. If we're using g of negative 2, then here we're saying that the a value we have is negative 2. So which one's going to be bigger? Your choices are, we can plug a 2 into this, see what we get for an answer, that's the remainder. We can plug a negative 2 in for this, see what we get, and that would be the remainder. Or we can actually do the division. Do either one. I happen to think, based on my last mistake for the previous problem, that the division is actually easier. So I'm going to do the division. So I'm going to divide synthetically by 2. Coefficients are 3, negative, whoops, I just made a huge mistake. This is not written in descending order. We want the exponents to go from biggest to smallest. And I'm not missing any terms, so that's fine. So my coefficients are negative 2, 3, 3, and negative 2. Add, multiply, add, multiply, add, multiply, remainder 0. So the first part is, which is greater, the value of g of negative 2 or the remainder when g of x is divided by x minus 2? Well, here we're saying the remainder is equal to 0. If I do the second part, I can do division again, or I can just plug the number into the function. I kind of think the division's easier. So the a value I'm using here is -2 because we're plugging the -2 in. So I add and I multiply and I add and I multiply and I add and I multiply. So what this is suggesting is that g of -2 is 20. And I would argue that this is much faster than plugging the -2 into here directly, doing it by hand. So to actually answer the question, which is greater? G of -2, which equals 20, is greater than the remainder of g of x divided by x minus 2, which is 0. Cool. That concludes the first half of the notes, and that is the remainder theorem.